Hello, welcome to week 1 of iTech 770, the online version. Today we're covering the foundations, what databases are and why healthcare needs them, and the coding systems that make healthcare data meaningful. By the end of this lecture, you'll understand why a simple spreadsheet can't handle the complexity of modern healthcare data. What is data? Data is raw facts and figures without any context. Look at these examples on the screen. John, 120/80, 315/85, J45.30. By themselves, these mean nothing. Is John a patient? A doctor? A medication? 120/80, is that a blood pressure or a ratio, something else? That date, is that a birthday, an appointment? Data alone has no meaning. It needs context to become useful. That's the key insight we're building toward. Databases don't just store data, they store them with structure and relationships that give them meaning. This is the DIKW pyramid: data, information, knowledge, and wisdom. It's a foundational concept in informatics. Let's trace a single data point through the pyramid. Data, 120/80, just numbers. Information, when we add context, this is Mrs. Johnson's blood pressure reading from today's visit, becomes information. Knowledge, a clinician looks at this and knows 120/80 is within normal range for an adult. That's knowledge, applying expertise to information. Wisdom, the patient decides no intervention is needed, but recommends continued monitoring given the patient's family history. That's wisdom, judgment applied to knowledge. Healthcare IT systems operate primarily at the data and information levels. Our job is to structure data so clinicians can efficiently turn it into knowledge and wisdom at the point of care. Here's why this matters. Healthcare is drowning in data. The average hospital generates 50 petabytes of data per year. To put that in perspective, 1 petabyte is 1,000,000 gigabytes. That's roughly equivalent to 500 billion pages of text per hospital per year. A single patient generates about 80 megabytes of structured electronic health record data annually. That doesn't include imaging, which can be gigabytes per study. And healthcare data is growing at 36% every year, faster than almost any other industry. The question isn't whether we need sophisticated systems to manage this data. The question is how we build systems that can handle this volume while maintaining accuracy, security, and accessibility. That's what database management systems do. What is a database? A database is an organized collection of structured data stored electronically, but that definition undersells it. Let me highlight 4 key characteristics. Persistent. The data survives after the program ends. Unlike variables in a program that disappear when you close it, database data stays. Organized. Data is structured according to a defined schema, not just dumped in randomly. Queryable. You can ask questions of the data and get answers, like show me all the patients over age 65 with diabetes. And shareable. Multiple users and applications can access the data simultaneously. So a database is not just a file, it's a managed system with rules, relationships, and controls. Before we appreciate what database gives us, let's remember what we escaped from. This image shows what medical records look like for most of the 20th century. Paper charts, filing cabinets full of them, folders stuffed with handwritten notes, sticky notes, all manner of confusing pieces of information. The problems were enormous. I remember a doctor in the first town that I practiced in who kept his medical records on 3x5 cards, and a patient visit might just say cold, penicillin, $3, and that was the medical record. So the problems obviously were enormous. And you can imagine the problem with locating records or losing charts. Charts would get misfiled. Once they're misfiled, it's virtually impossible to find them. Or somebody might borrow a chart and never return it. Things got lost. And that doesn't even begin to cover the illegible handwriting. I remember as a freshman in medical school, I got an A in the second semester. The first semester was Standing on a Pedestal 101, but the second semester was Illegible Handwriting 102. I made an A+. So that's a big issue in medical records. It's locating the data and then being able to interpret it when the handwriting is so awful. And there was no backup. If something happened, there was a fire or a flood, destroyed records are destroyed permanently. They're never found again. And it's also very slow to retrieve data. Finding a specific laboratory result from 3 years ago inside one of these thick charts meant manually searching page by page through inches and inches of paper. So, in 1999, the Institute of Medicine report, To Err is Human, estimated that nearly 100,000 Americans die every year from preventable medical errors, many related to information problems that better systems could have prevented. Paper wasn't just inefficient, it was dangerous. Some of you might be thinking, okay, paper's bad, but what about Excel? Can't spreadsheets handle healthcare data? Well, for some small data sets, yes. But at scale, spreadsheets fail in critical ways. There's no data integrity. Nothing stops you from entering the same patient twice, or entering male in one row and M in another. Duplicate patients' records are a major safety issue. Also, there are no relationships. In Excel, you can't naturally link a patient to their visits, to their diagnoses, and to their medications. Everything is just flat. Also, there's no concurrent access. In an Excel spreadsheet, if you have the spreadsheet file open, someone else can't edit it. So in a hospital where sometimes dozens of people need access to the same patient's record, it's impossible. Also, there are no security controls. Anyone who can open the file can see everything that's in it and edit it and change values. There's no way to say nurses can see clinical data but not billing data. Spreadsheets are great tools, but they're not database systems. Healthcare requires much more. So this brings us to the Database Management System, the DBMS. DBMS is a software that sits between the users and the actual data. Think of it as a sophisticated middleman. Look at the diagram. Users and applications on the left, the database on the right, and the database management sits in the middle, managing all the interactions. Users never touch the raw data directly. They send requests to the database management system. Give me this patient's medications. The database management system validates the request, checks permissions, retrieves the data, and sends it back to the requester. This architecture is what enables security, integrity, and concurrent access. The database management system is the gatekeeper. Every database management system performs 4 fundamental operations, collectively called CRUD, C-R-U-D. C is for create. Create is to add new files or new records. A new patient registers, we create a patient record. R is for read, the ability to retrieve data. A physician looks up a patient's history. The U is for update. That allows us to change values, modify existing records. A nurse updates vital signs. And the D in CRUD is delete. That's to remove records. This is uncommon in healthcare. We usually think of records as inactive rather than being deleted because sometimes they're needed for historical reasons or even legal reasons. So every healthcare application you'll ever work with, like Epic or Cerner, or your hospital's lab system, the billing system, all of them are performing these 4 operations against a database, thousands of times per second. Understanding CRUD is understanding the heartbeat of health information technology systems. So beyond CRUD, a database management system handles several critical responsibilities. Data storage and management, efficiently storing data on disk, managing the memory, optimizing access patterns. And they also do data integrity enforcement, ensuring rules are followed. A patient ID must be unique. A date of birth must be a valid date. They also perform the security and access control, authenticating users, authorizing what they can see and can do, logging in who did what. They perform the backup and recovery, automatic backups, ability to restore to a certain point in time if something disastrous goes wrong. They also handle concurrent access, managing what happens when two users try to update the same record in the same field simultaneously. And lastly, they do query optimization, taking your request and finding the fastest way to execute it across sometimes millions or billions of records. This is why we don't just use files or spreadsheets. A database management system is a sophisticated piece of software that handles all this complexity for us. Let's get specific about why healthcare needs a database management system. First, data integrity. Duplicate records are a major problem. The American Health Information Management Association estimates that 12% of hospital records are duplicates. That means the same patient exists multiple times in the system under slightly different names or identifiers. Well, why is this dangerous? Well, imagine a patient comes to the emergency room unconscious. The emergency room physician looks up John Smith, date of birth 3/15/85, and finds a record that shows no drug allergies. But there's another record for Jonathan Smith, same date of birth, 3/15/85, that lists a severe penicillin allergy. Different entry format, but the same person. So a database management system prevents this through primary keys and what's called unique constraints. That means that primary key has to be unique, and there can only be one per patient. So the medical record number, or the MRN, is enforced as unique. The system won't let you create a duplicate. This is data integrity in action. Second reason, HIPAA isn't optional. It's the federal law. So we are going to implement HIPAA regulations. They have to be done at the database management system level. A database management system provides the infrastructure to comply with the HIPAA laws. These include things like user authentication. You must log into the system. The system knows who you are and whether you have authority to access certain pieces of information. It also enforces role-based access control. A nurse sees different data than the billing clerk. A physician sees more than a medical assistant. These roles are defined in the database management system. The database management system also allows for audit logging. So every access is logged. If there's a breach investigation, we can go back and see exactly who viewed which records and when. And lastly, they do encryption. Data is encrypted both at rest on disk and in transit over the network. Anytime data is moved, it's encrypted so that someone that is trying to hack into the data can't just read the data without knowing the security keys. Just think, try to implement all of these things in Excel. You just can't. Security requires a real database management system. And thirdly, concurrent access. Picture a busy emergency room. The ER physician is reviewing the patient's history, and the nurse is documenting vital signs. The lab tech is entering some results. The pharmacist is checking the medication orders, and the registration clerk is updating insurance information. All of these people are accessing and potentially modifying the same patient's record simultaneously. Without a database management system managing this, you get chaos. Lost updates, corrupted data, system crashes. The database management system handles locking, transactions, and consistency to ensure everyone can work on the same data without stepping on each other. This is called concurrency control, and it's something databases do that file systems simply cannot. Fourth, and perhaps most important, relationships. Healthcare data is inherently relational. A patient has visits, Each visit has diagnoses, procedures, orders. Orders become results. Medications are prescribed, dispensed, and administered. This chain of relationships is what makes healthcare data complex and powerful. With properly related data, I can ask questions like, show me all the diabetic patients over 65 who haven't had a hemoglobin A1C test in the past 6 months. That query touches patient demographics, problem lists, lab orders, and lab results, all connected through relationships. A database management system maintains all these relationships through foreign keys, which we'll see shortly. So that's a key concept, a foreign key. This is what transforms isolated data points into a coherent patient story. There are several types of database models. Let me give you the landscape. First, there are the hierarchical databases. These go back to the very beginning. They were big in the 1960s. Data is organized like a tree, and some legacy hospital systems still use this structure. Then came the network databases in the 1970s, which allowed more flexible connections than hierarchical. Then we came to the big daddy, the relational databases, which emerged in the 1980s and dominate today. The data is all stored in tables connected by keys, and this will be our focus for this course. And finally, we have object-oriented databases that store objects directly. These are niche use cases, and we'll discuss them briefly, but that's not the main purpose. That's not the most common use in database management systems. And finally, we have these NoSQL databases. These are the modern alternative that stores documents and key value stores and graph databases. Good for certain specific use cases, but most healthcare systems still use the relational database. Why relational? Because healthcare data has clear entities like patients, encounters, visits, orders, results, with clear relationships among them. The relationship model fits this naturally. The relational model was invented by Edgar Codd at IBM in 1970. His paper, A Relational Model of Data for Large Shared Data Banks, is one of the most influential papers in computer science history. The key insight: data should be organized in tables called relations. Tables are connected through keys, and you interact with the data using a standard language, SQL, Structured Query Language, SQL. This model is the foundation of Oracle, SQL Server, MySQL, Postgres, and virtually every major healthcare systems database. When you learn relational databases, you're learning the dominant paradigm in health information technology. Let's nail down the terminology. These terms are used interchangeably, which can be confusing. A table is also called a relation. It's the same thing. A row is also called a record or a tuple. Same thing, one instance of data. A column is also called a field or an attribute. Same thing, a property of the data. When I say each record in a patient's table, and your textbook says each tuple in the patient relation, we mean the same thing. For this course, I'll mostly use table, row, and column, the common industry terminology. Here's a concrete example, a patient's table. Look at the structure. Patient ID, 101, 102. This is our unique identifier. First name, last name, John Smith, Maria Garcia. Date of birth, DOB. Gender, MF. Each column is an attribute describing something about a patient, and each row is one patient's record. This is the fundamental building block of relational databases, a table of rows and columns. Simple in concept, but powerful when you connect multiple tables together. The primary key is one of the most important concepts in database design. A primary key is a column, or a combination of columns, that uniquely identifies each row in a table. And there are two fundamental rules. It must be unique. In order to locate a specific record, there has to be only one correct answer. There can only be one row that has a given ID, because otherwise you get confused when you try to retrieve a specific record. And secondly, it cannot be empty. It cannot be null. It cannot have no value. In a database management system, every record, every row must have a value for the ID, for the primary key. So in healthcare, common primary keys include like a patient ID or medical record number for patient tables, or for doctors, we use the National Provider Identifier, the NPI. For a visit, you might have a visit ID that's assigned by the facility, or an encounter ID. So the types of primary keys are highly variable and are appropriate for given situations. Look at the highlighted column in this table, patient ID. Every patient has unique ID. This is how we unambiguously refer to a specific patient across the entire system. If primary keys identify rows within a table, foreign keys connect tables to each other, and this is a very important concept. The primary key concept is very simple, but foreign keys is a little bit more complex. A foreign key is a column in one table that references the primary key at another table. Let's look at a specific example. The visits table has a column called patient ID. This is the foreign key. It references the patient ID primary key in the patient table. The arrow shows the relationship. Each visit belongs to a patient. By storing the patient ID in the visits table, we create a link between them. And this is how relational databases represent relationships. Foreign keys are the glue that connects multiple tables. Let's see this in a larger picture. Here we have three tables: patients with primary key patient ID, visits with primary key visit ID and foreign key patient ID, and thirdly, the diagnosis table with primary key diagnosis ID and foreign key visit ID. Follow the arrows. A patient can have many visits, a one-to-many relationship. A visit can have many diagnoses, another one-to-many relationship. This chain, the patient to visit to diagnosis, is how we trace a patient's clinical history. Next week, we'll formalize this with entity relationship modeling, modeling, ER relationships. For now, understand that foreign keys create these connections. All right, let's survey the market. What database management systems options exist? You've got commercial options. For example, the biggest in the country is Oracle Database, the 800-pound gorilla in the room. Enterprise-level features, but also enterprise price. Many large healthcare systems use Oracle. Then you've got Microsoft SQL Server. It's popular in the Windows environments. It has a strong integration with Microsoft tools. And then there's also IBM DB2, which has been around since the 80s. And some legacy systems, especially in large hospitals that used to have mainframes, they still have a relationship and connection to IBM DB2. Now we have some open source options emerging, like Postgres. This has many of the enterprise grade features, but they're completely free rather than Oracle. And that's the choice that we're going to use for this course. We will be teaching you a little bit about Postgres, and we'll be doing some coding in Postgres. So it's an example of an SQL-like system like Oracle's SQL, very similar in concept and capabilities, but you can use it for free. Then there's MySQL, or MySQL. It's popular for web applications. Oracle has assumed control of MySQL. It was independent for a while. And then there's a new fork of the SQL tree called MariaDB, which is community-driven and open source. The open source options have matured dramatically. Postgres in particular rivals Oracle in its features while costing nothing. So why do we use Postgres specifically? Well, first, like we said, it's open source. There are no licensing costs. And for a health tech startup or a research project, this can matter enormously. And secondly, it has enterprise features. It has ACID compliance for transaction integrity. It has advanced security features, including row-level security. And it has excellent JSON support, which matters for FHIR-based interoperability. So if you want to communicate among various systems, you need to have the FHIR interoperability interface capabilities. So Postgres allows you to do full text search for clinical notes. It's extensible for custom healthcare data types. And thirdly, it can be configured for HIPAA compliance. Postgres itself doesn't make you HIPAA compliant. That requires proper implementation, but it provides the necessary security infrastructure. And fourth, there's a large community for support and resources. You won't be struggling alone. In Postgres, is Postgres actually used in healthcare? Of course. Major health systems and academic medical centers use Postgres for research databases and data warehouses and custom applications. Healthcare startups often choose Postgres because it's free and scales well. Many clinical trial management systems run on Postgres. Also, government health agencies, including some of the NIH and CMS, CDC, use Postgres. Beyond healthcare, Postgres handles a massive scale. Apple, Spotify, Instagram, Reddit, all use Postgres. If it can handle Reddit's traffic, it can handle your hospital data. The point is you're learning an industry-relevant, production-grade database system. Here's a quick comparison. Look at this table. Cost. Postgres and MySQL are free. SQL Server and Oracle can cost thousands to millions for licenses. HIPAA ready. All of them can be configured for HIPAA. This is about implementation, not the software itself. JSON FHIR support. Postgres has excellent native JSON support, which helps with FHIR resources. And community. Postgres, SQL, and MySQL have large open source communities. SQL Server and Oracle have vendor support, but you have to pay for it. For this course, Postgres gives us everything we need at no cost. In your career, you're likely to encounter all of these systems. So let's recap part one. Data needs organization. Raw data without structure is meaningless and dangerous in healthcare. Database management systems provide the infrastructure we need to implement integrity, security, concurrent access, and relationships. We will focus on the relational model, which uses tables that are connected by keys, both primary keys, which have unique identification, but also foreign keys for relationships among tables. Postgres is our tool, enterprise grade, open source, and healthcare ready. So next we'll explore the healthcare coding systems that give meaning to the data we store. These codes, like the ICD-10, CPT, and SNOMED-CT, are the vocabulary of healthcare databases. Good evening, or whatever time it is for you. We're going to shift gears. We've talked about the container, the database, but now we're going to talk about what goes in it, healthcare data, and the coding systems that standardize it. Let me set up the problem with a scenario. A patient sees a doctor in South Carolina and gets diagnosed with a heart condition and receives treatment. 2 years later, they move to New York and see a new cardiologist. How does the New York doctor understand what happened in South Carolina? Different EHR system, different hospital, different state. The answer is standardized coding systems. When both systems use the same codes for diagnoses, medications, and procedures, the data becomes portable and understandable regardless of where it originated. Without standardization, we have a Tower of Babel. Everyone speaking different languages, unable to communicate. Standardized codes enable several critical functions. Number one, interoperability. Different systems can exchange data meaningfully. Your EHR can receive records from another hospital and understand them. Two, the billing accuracy. Insurance companies require specific codes. Wrong code, wrong payment, or no payment. Thirdly, there's quality measurement. How do we compare outcomes across hospitals? By using the same codes to define conditions and procedures. Thirdly, research. Aggregating data across institutions requires standard definitions. Diabetes must mean the same thing everywhere. And fourthly, the public health. How does the CDC track disease outbreaks? Through standardized diagnostic codes reported from hospitals nationwide. So coding isn't just bureaucratic overhead, it's the foundation of a functional healthcare system. Healthcare has many coding systems, each serving a different purpose. And let me map the broad landscape. First, you have diagnoses. The standard in America is International Classification of Diseases, the 10th version, CM. Then we have SNOMED, that's for diagnosis. And we also have an international system called SNOMED, which is systemized nomenclature in medicine, current terminology. And then for procedures, the standard in America is the current procedural terminology for outpatients. For inpatients, they use a thing called ICD-10 PCS. For equipment and supplies, there's a nomenclature called HCPCS. So we've got so many different systems for different use cases. In the laboratory, the standard is LOINC, L-O-I-N-C, which comes from the Regenstrief Institute in Indianapolis. For medications, there are two commonly employed coding systems, the National Drug Classification, or NDC, and there's another one called RxNorm. Then for clinical concepts, we go back to our SNOMED, Systematic Nomenclature in Medicine, covers all the vocabulary of medicine. I know this can feel overwhelming, and here's the key insight. Each system has a specific purpose. ICD-10 is for billing diagnoses, CPT is for billing procedures, SNOMED-CT is for clinical documentation. Understanding the purpose helps you know which code set is appropriate. We're covering this in two parts. This week, this is week 1, we're going to cover ICD-10, the diagnosis coding system, and CPT, the procedure coding system. We'll also talk a little bit about SNOMED-CT, clinical terminology. Those three are the biggies. Those are the main coding systems that we use in medicine. But next week we'll go into a little bit more depth in the laboratory test codes, the LOINC, L-O-I-N-C, medication codes, the NDC, National Drug Classification, and plus entity relationship modeling, ER modeling, which will show how these codes fit into a database design. By the end of next week, you'll understand the full picture of healthcare data standards. Let me show you how to put these codes together in practice. Let's follow this little flow chart we have here. A patient presents with a complaint. Say, I have chest pain. The provider examines the patient and documents the encounter. The provider assigns diagnosis code I-10 for hypertension, I-25.10 for coronary artery disease. The provider performs procedures 99214 for a moderate office visit and a 93000, an electrocardiogram. The claim is submitted to the insurance company with these codes, and the insurer pays based on those codes submitted. The diagnosis codes justify medical necessity. The procedure codes describe what was done. Together they determine reimbursement. Coding literally drives revenue in healthcare. Let's dive deep into ICD-10, starting with some history. ICD-10 has a surprisingly long history. Way back in 1893, the International List of Causes of Death was created, originally for tracking mortality statistics. Then fast forward to 1948, the World Health Organization took over and expanded it to include diseases, not just causes of death, and it became the International Classification of Diseases. ICD-10 was used in the United States from 1979 to 2015 for 36 years. ICD-10 was implemented in the US on October 1st, 2015. It had been used in Europe for quite some time. ICD-11 was released by the World Health Organization in 2022, but the United States has not yet adopted it. The transition is probably years away. There's so much invested in the current coding systems that making the transition to a new version is very difficult and will be postponed. When we talk about ICD-10 in the United States, we typically mean ICD-10-CM, the clinical modification, which we will discuss in a little bit more depth a little later. So transitioning from the ICD-9 to ICD-10 was a massive undertaking. ICD-10 had approximately 14,000 codes. ICD-10-CM has 70,000, a five-fold increase. So why do they have so many more codes? Do you think we have that many more diseases? No. It was for specificity. Here's an example. In ICD-9, there's essentially one call for code for having a fall. In ICD-10, there are codes specifying where did you fall? Was it on the stairs, a ladder, a playground, a bathtub? What were you doing? Walking, running, skating, playing football? Was it intentional, accidental, self-harm, assault? The initial encounter, or is this a follow-up visit? This specificity enables better tracking of injury patterns, but also means coders need much more training. The transition cost the U.S. healthcare system billions of dollars. There are actually two ICD-10 systems in the United States. The ICD-10-CM clinical modification is used for diagnosis coding and is used by virtually all healthcare providers. And it's maintained by the Center for Disease Control's National Center for Health Statistics. There's also the ICD-10 PCS procedural coding system, which is only used for inpatient hospital procedures, and it replaced ICD-9 Volume 3, which had procedure codes. And this is maintained by the Centers for Medicare and Medicaid Services, CMS. So CMS is maintaining this version of this portion of the ICD-10 codebook, the procedural coding system. ICD-10 PCS is maintained by CMS. In this course, we'll focus predominantly on ICD-10-CM diagnosis codes for the clinical. If you work in a hospital inpatient coding, you will also need to become familiar with ICD-10 PCS, the procedural codes. What is ICD-10-CM actually used for? Well, predominantly for insurance billing and claims. This is the primary use. Every claim submitted to Medicare, Medicaid, or commercial insurance companies requires an ICD-10-CM diagnosis code to justify the claim. It's also used for epidemiological tracking. The Centers for Disease Control, the CDC, uses aggregated ICD-10 data to track disease prevalence and trends throughout the country and the world. It's also used for quality measure reporting. Many quality measures are defined using ICD-10 codes. What percentage of your diabetic patients have controlled hemoglobin A1C levels? It requires identifying diabetic patients via their ICD-10 diagnosis codes. It's also useful for clinical documentation. The codes become part of the medical record. So ICD-10-CM is required. You cannot bill Medicare without it. It's mandatory for all HIPAA-covered entities. Let's look at how ICD-10-CM codes are structured. Codes are 3 to 7 characters long. The first character, character 1, is always a letter, A through Z, except U's been reserved. Character 2 is always a number. Character 3 can be a number or a letter. And characters 4 through 7 add additional specificity separated by a decimal place after the third character. In the first 3 characters, they define the category. Characters 4 to 7 add specificity, like the body location or the severity or laterality episode of care. They just help specify in more detail the clinical situation. Codes must be assigned to the highest level of specificity available. If a 7-character code exists, you can't bill with just 3 characters. This is important for billing because this gives the insurance companies opportunities to deny claims if you haven't given the full specificity available. So let's break down a specific code. How about E11.65? The E letter tells us which chapter out of the ICD-10 book it is, and E is endocrine, nutritional, and metabolic diseases. 11 is the code for type 2 diabetes within the chapter. The decimal point separates the letter and number from the other characters. Then the 6 indicates with complications. The 5 specifies the complication is hyperglycemia. So E11.65 means type 2 diabetes with hyperglycemia. Notice how the code builds from a general to specific. The E chapter, E11 the condition, E11.6 with complications, E11.65 specifically the complication hyperglycemia. It all makes perfect sense. Now ICD-10 CM is organized into 21 chapters by body system or condition type. Here are some of the key chapters that you'll be familiar with. A 00 through B99 are all the infectious and parasitic diseases. C00 through D49 are neoplasms or cancers. E00 through E89 are endocrine, nutritional, and metabolic diseases, and that's where diabetes is, which is the biggie in that group. I00 through I99 are diseases of the circulatory system, which include heart disease and hypertension. Hypertension is the big one there. J00 through J99 are diseases of the respiratory system, which include bronchitis, upper respiratory infections, pneumonia, COPD. M00 through M99 are musculoskeletal system, like back pain, arthritis. S00 through T88 are injuries, or poisoning, or external causes of disease. So when you see a code, the first letter immediately tells you the general category, like the I codes are cardiovascular, the E codes are metabolic. This is very helpful when you're navigating. Let's look at the single most common diagnosis code in primary care. That's I-10. What is I-10? Essential or primary hypertension. So it's hypertension not otherwise specified. This is basic high blood pressure without additional complications. Notice it's only 3 characters. No additional specificity is needed or available for uncomplicated essential hypertension. But there are some related codes, like I-11, hypertensive heart disease, hypertension with heart involvement, or I-12, hypertensive chronic kidney disease, or I-13, hypertensive heart and chronic kidney disease. These get more specific with additional characters. So I-11.0 is hypertension heart disease with heart failure. I-12.9 is hypertensive chronic kidney disease with unspecified stage of the kidney disease. So you'll see that I-10 constantly in the primary care data sets. Now, diabetes coding shows the complexity of ICD-10. The base code, E11, means type 2 diabetes. But E11 alone is rarely used. You need to specify complications or lack thereof. For example, E11.9, type 2 diabetes without complications. This is the baseline code used very, very frequently. But it specifies that it is without complications. E11.65 is diabetes type 2 with hyperglycemia, which means the blood sugar is high. E11.21 is diabetes with diabetic nephropathy with kidney involvement. E11.4 is diabetic neuropathy, unspecified, so that means a problem with the nerves like numbness or pain or burning. E11.621 is diabetes with a foot ulcer. So you can see how the code, as we get further and further specificity, it is able to tell you much more about what's going on with the patient. A long way from just diabetes. So a single diabetic patient might have multiple E11 codes, like E11.65 and E11.40, and E11.621 if they have uncontrolled sugar, neuropathy, and a foot ulcer. This is the specificity ICD-10 entails and requires. Injury codes are where ICD-10 gets really specific. Look at this code, S52.501A. S52.501A. Let's break it down. S52 means a fracture of the forearm. The .501 says the lower end of the right radius, unspecified type. A means the initial encounter for this condition. That seventh character, the A, which can be an A, D, or S, is important. A is the initial encounter, D is a subsequent encounter, and S is for the sequela, that a long-term complication or a late effect of that injury. So if a patient comes back for a cast check, you code it as a S52.501D. If they develop arthritis in the wrist years later as a result of the fracture, you could add the S addendum to it. So it would be S52.501S. This level of detail lets us track injury patterns, treatment patterns, and outcomes. Here's a reference table of codes you'll see constantly in primary care data sets. What we often use in the office, we call them cheat sheets, that have the most common things that we encounter, so that we don't have to go through long books, coding books, to try to find the proper entities. So if you're working with primary care data, these codes will dominate your data set. They represent the chronic conditions, hypertension, diabetes, high cholesterol, depression, that primary care providers manage. So how do these codes appear in the database? Here's a typical diagnosis table. You have your diagnosis ID, the visit ID, the ICD-10 code, and a description. So we have I-10, essential hypertension, E11.9, type 2 diabetes. So these are multiple diagnoses for a given patient. The diagnosis ID, the primary care, is a unique identifier for each diagnosis record. The visit ID is a foreign key links to the visits table. The ICD-10 code is the standard ICD-10 code for the diagnosis, and the description is some readable text that allows somebody that's looking at this data to not have to look up all the codes to find out what they were, so you can actually store it multiple times. So one visit can have multiple diagnoses. That's why we have a separate diagnosis table rather than putting diagnosis codes directly into the visit table. This is a relational design in action. I mentioned the ICD-10 PCS for the procedures. Let's give you another example how this is used. The ICD-10 PCS is used only for inpatient hospital procedures like surgeries and significant interventions performed only during a hospital stay. Codes are 7 characters, all alphanumeric, with a very structured format. Includes the section, the body system, the root operation, the body part, approach, device, and qualifier. Here's an example. 0BJ08ZZ, a diagnostic bronchoscopy. For outpatient and physician procedures, we use CPT instead. So if you do a bronchoscopy in the hospital during an admission, it's an ICD-10 PCS code. The same procedure in an outpatient clinic, we use the CPT lexicon. You don't need to memorize the ICD-10 PCS for this course, but know that it exists and where it's appropriate. Let's shift to CPT, how we code what was done to the patient, not just what's wrong with them. CPT stands for Current Procedural Terminology. Here are some key facts that you need to know about the CPT and its history. It is actually maintained by the American Medical Association. It was first published in 1966. It's updated annually. New codes are released each January. It's copyrighted, unlike ICD-10. CPT is copyrighted by the AMA, and you can't freely distribute the codes. The AMA's copyright is somewhat controversial. Healthcare providers must use CPT for billing, but they may also pay the AMA for access to the code definitions. This is a significant industry cost. CPT provides standardized codes for medical procedures and services, for surgical procedures, and diagnostic tests and services. It's used for billing to the insurance companies and processing claims and tracking utilization, what services are being performed. HIPAA designates CPT as a required code set for electronic transactions. If you submit an electronic claim, you must use CPT codes for the procedures. Think of it this way. ICD-10 answers, what's wrong? CPT answers, what'd you do about it? CPT codes are primarily 5-digit numeric codes. There are 3 categories. Category 1, the main codes, which start at number 100 and go up to 99499. This is what most people mean when they say CPT code. But Category 2 are performance measurement codes ending in ending in F. These are optional codes used for quality tracking. And Category 3, temporary codes for emergency technology ending in T, used for new procedures that haven't been included in the Category 1 code set. For this course, we'll focus in on the Category 1 codes, the standard procedure codes used for billing. Category 1 codes are organized by type of service. And so let's look at how it's broken down by numeric ranges, starting from 00100, so code 100, all the way up to 01999. These are all anesthesia services. Codes that start with 1, so starting at 10,000, going up to 69990 are all surgery procedures. Then the 7s, 70010 through 79999, are radiology codes, like for X-rays, CAT scans, MRIs, ultrasounds. Then the 8 series codes are for pathology and laboratory. Those are your blood tests and biopsy codes, going from 80047 to 89398. Then the one that I was most familiar with were the 9 codes, 90281 through 99199, are all your office visits and things that physicians do, the medical codes. Then there's near the end of the 99s, the 99202 through 99499 are what are called the E&M codes that are used extensively. These are office visits and comprehensive physical exams and well checkups. These are the most common codes used by primary care and outpatient medicine. So the most commonly used codes in primary care fall into 2 areas, the 99202 to 99499, the E&M codes that we were just talking about. And they also include some consultations and hospital visits. And then the also most commonly employed codes are the 8 series for blood tests and lab tests, 80047 through 89398. Understanding these ranges help you navigate the code set tremendously. It makes it obvious what's being done. So the E/M stands for evaluation and management, the E&M codes. These codes cover the thinking service, the visit itself, not the procedures. So E&M codes are used for office visits for both new and established patients, hospital admissions and consultations, emergency department visits, telehealth encounters. So E&M codes are very common, used a lot. In primary care, E&M codes are by far the most frequently billed codes. A family physician might bill on 99213 and 99214 all day long, and may be almost the only codes that they use. These represent the core intellectual services that physicians provide. E&M codes come in levels based on complexity. For established patient office visits, we have 99211, which is a minimum complexity visit. Sometimes just a nurse can do it, does not require the presence of the doctor. Then we move up 1 from 99211 to 99212. This is a low-level office visit, a very straightforward. And this is not used very often because it's very minimum. It's just a few minutes of the doctor's time. Then we moved up to the more common. The most common office visits are either 99213 or 99214. 99213 is low complexity, the standard office visit. 99214 is a moderately complex office visit that takes a little bit more time and thinking. Then there's the biggie, 99215, a high complexity visit that may take an hour the doctor's time for a severe unstable condition, employing extensive decision making. So the higher level means more complex medical decision making and, of course, associated higher reimbursements. A 99215 pays roughly twice what a 99212 pays. E&M coding guidelines changed significantly in 2021 and simplified considerably. Previously, E&M level was determined by counting elements of history, exam, and decision making. Physicians spent enormous time documenting to check the boxes to be sure they qualified for the code that they were billing for. In 2021, the guideline shifted to two options: medical decision making, MDM, based on complexity of problems, the data reviewed, and the risk of the management process, and time, the total time spent on the encounter, including documentation and care coordination. So this was a major improvement. Physicians can now focus on the patient rather than the documentation checklists. MDM complexity is what should drive the code levels. Let's look at a typical 99214. This is an office visit for an established patient with moderate medical decision-making complexity. A typical 99214 scenario: a diabetic patient comes in for follow-up. You review the recent lab results, discuss medication adjustments, address their blood pressure, which is also elevated, counsel on diet. This patient has multiple chronic conditions, moderate data review, and moderate risk. The reimbursement for 99214 is roughly $110 to $130 depending on the payer and region. This might seem low for 20 to 30 minutes of a physician time when you consider their overhead, but this is what the current market bears. Here are some common CPT codes that are used beyond just the E&M codes that we've discussed at length. Let's look at 36415, venipuncture, drawing blood. 71046, chest x-ray, 2 views. 93000, electrocardiogram with interpretation. 90471, immunization administration. 90658, an injection for the flu vaccine. Notice that the immunization requires two codes, one for the vaccine product, like in this case the 90658, and one for the actual administration, the 90471. This is common in CPT, separating the thing from the doing. Modifiers are two-character additions to the CPT codes that provide additional information. Common modifiers include 25, which means significant but separately identified E&M service. So use this when you bill an office visit and a procedure that was performed on the same day. Then there's the modifier 59, which means a distinct procedural service that indicates the procedure is separated and not bundled, so that the insurance company doesn't try to just pay for one thing and then say not pay for the other, because assuming that it's included in the billing for the previous service. There's also the addendum of LT and RT for left side and right side for times when we do bilateral procedures. And then 76 is a repeat procedure by the same physician. So if somebody is cutting off multiple skin tags, when they add the 76, it says it's a repeat procedure by the same physician. We know that the billing code was already included. Now you're seeing the billing code again. This is to tell the insurance company that this one's different from the other one, even though it's the same code. And so please provide some reimbursement. So modifiers affect reimbursement immensely. If you use them correctly, you get paid appropriately. If you use them incorrectly, and you're going to be accused of fraud or at least denied payment. This is an area where coding expertise really matters. Here's the key in integration point. A complete claim requires both ICD-10 and CPT. What is the ICD-10? That's your medical necessity. Why was the service needed? That's your diagnosis. CPT provides the service. What was actually done? Here's a couple simple examples. Diagnosis E11.65, type 2 diabetes with hyperglycemia. Procedure 99214, office visit of moderate complexity. Procedure 82947, a blood glucose test. The payer looks at this and says, does the diagnosis justify the procedure? Diabetes justifies a glucose test. If you build a glucose test for a patient with only a diagnosis of back pain, the claim might be denied. This linkage, diagnosis to procedure, is the core logic of healthcare billing. Here's how CPT codes appear in a database. Got a procedure ID, the visit ID, the CPT code, and a description. In the first line, we've got a 99214, an office visit. You got a 36415, a venipuncture. The structure mirrors the diagnosis table. You got your procedure ID, the primary key, the visit ID, the foreign key to the visit, the CPT code, the standardized code, and the description that came out of a major a file that allows you to pull the text so that people that are trying to read these data can look at them, but it doesn't have to be stored because it's redundant. It's implicit in the codes. So once again, you can, again, a visit can have multiple procedures, and now you can see how to join the patient to the visit, to the diagnosis, and the procedures. The relationships enable comprehensive analysis, and we will spend a lot of time during the semester looking at these relationships and how we have primary keys and foreign keys that allow us to link the various data together on behalf of the patient. Our final coding system for today is called the SNOMED-CT, a very different kind of system from the ICD-10 and CPT. And with that, I'm going to take a little break. SNOMED-CT stands for the Systematized Nomenclature of Medicine Clinical Terms. It's the most comprehensive clinical terminology in the world, over 350,000 concepts covering diseases, findings, procedures, body structures, organisms, substances, and more. It's maintained by an organization called SNOMED International, which is a nonprofit. Unlike International Classification of Diseases version 10, ICD-10, and CPT, current procedural terminology, SNOMED-CT is not primarily a billing code set. It's a clinical terminology, a language for describing clinical reality in a structured form. SNOMED has evolved significantly. In 1965, SNOP, or Systemized Nomenclature of Pathology, started as a pathology coding system. In 1974, it was expanded to SNOMED, covering more than just pathology. In 2002, it merged with the United Kingdom's clinical terms to create SNOMED-CT. This was a major leap in comprehensiveness. Today, it's used in over 80 countries, and is required for U.S. electronic health record certification under the Meaningful Use Promoting Interoperability. The merger with the United Kingdom with the British clinical terms brought in a huge lexicon of primary care terminologies and concepts that the original SNOMED lacked. The original orientation was more towards pathology, and so it had lots of terminology and detail, but didn't have commonly encountered terminology. So this made SNOMED-CT truly comprehensive across all care settings. This is a critical distinction. SNOMED-CT and ICD-10 serve different purposes. ICD-10 is a classification system. It puts things into categories for counting and billing. It's like a filing system. Where does this record go? Whereas SNOMED-CT is a terminology. It describes clinical reality with precision. It's like a dictionary. How do I accurately describe what I am seeing? Like for analogy, if I ask, where should we file this patient's chart? That's an ICD-10 concept. If I ask, how do I describe exactly what's wrong with this patient? That's SNOMED-CT. Both are valuable. They serve complementary purposes. Where is SNOMED-CT used? Well, primary electronic health record documentation, the structured problem lists, allergies, procedures in the electronic health record. For clinical decision support, rules that fire based on SNOMED-CT coded conditions. If the patient has SNOMED code for diabetes and a SNOMED code for pregnancy, alert the physician. That's a simple set of rules. It's also used in analytics and research. Precise cohort identification. Please find all the patients with exactly this type of pneumonia. It's also useful in health information exchange when sending clinical summaries between systems. SNOMED-CT is not typically used for billing. That's ICD-10 and CPT's domain. SNOMED-CT has a fundamentally different structure than ICD-10. There are three core components. First, concepts, a unique unit of meaning. Each concept has a numerical identifier. Secondly, there's descriptions, human readable terms for concepts. Each concept can have multiple descriptions. And thirdly and finally, relationships, links between the concepts, primarily is a hierarchical relationship. This structure enables rich semantic relationships. Viral pneumonia is a pneumonia, is a respiratory infection, is a infectious disease. You can traverse these hierarchies for analysis. Let's break down the SNOMED-CT concept. Concept ID 383-41003. This is a unique numeric identifier. Unlike ICD-10, there's no meaning embedded in the numbers. What you get instead is a fully specified name, the FSN, which comes out in that case to be hypertensive disorder, a disorder. This is the unambiguous complete name. The semantic tag, disorder, clarifies what type of concept this is. Then there's the preferred term, hypertension. This is what clinicians typically use, a shorter, common term for the same number. Synonyms, high blood pressure, HTN, hypertensive disease, alternative terms that all map to the same concept number. The power is that all these terms, hypertension, high blood pressure, HTN, resolve to one concept ID, 383-41003. SNOMED-CT is organized into hierarchies. Top-level categories include clinical findings, procedures, body structure, organism, substance, pharmacological product. So we've got the diseases and the symptoms and diagnosis. You got the clinical procedures. You've got anatomical structures, organisms like germs, and substances like medications. So all of those things are into different categories. Each of these branches into increasingly specific concepts, like a body structure may go to cardiovascular, might go to heart, might go to heart valve, might go to mitral valve. All of those are coming down the tree structure. This hierarchy enables powerful queries, like find all the patients with any cardiovascular disease by querying the parent concept and all of its descendants. Let's trace hypertension through SNOMED-CT. The concept ID 383-41003, fully specified name, hypertensive disorder. PT, hypertension. So the hierarchy path is a clinical finding and a disease and a disorder of the cardiovascular system, hypertensive disorder. So this concept has parent concepts and child concepts. If I query for all patients with disorder of cardiovascular system, which is a higher level concept, I'll capture all hypertensive patients plus those with heart failure, coronary artery disease, etc. The hierarchy enables flexible querying. SNOMED-CT is far more granular than ICD-10. For hypertension, ICD-10 just has I-10, essential hypertension. That's it for uncomplicated hypertension, one code. SNOMED-CT has dozens of specific concepts from essential hypertension, malignant hypertension, white coat hypertension, masked hypertension, resistant hypertension, hypertension in pregnancy, hypertension associated with organ transplant, and on and on and on. Many electronic health records use both SNOMED-CT and ICD-10. For clinical documents, you use SNOMED-CT, selecting the precise term that matches the clinical reality, and then system maps this to ICD-10 automatically for billing purposes. The National Library of Medicine maintains official maps between SNOMED-CT and ICD-10. These maps aren't always one-to-one. Multiple specific SNOMED concepts might map to one broader ICD-10 code, and that's fine. SNOMED captures the clinical detail. ICD-10 handles the billing categories. Where does SNOMED-CT appear in an electronic health record? Well, in the problem list, the patient's active and historical conditions. also among their allergies, drug and environmental allergies, among the procedures that have been performed, like past surgeries and interventions, in the category in the section on family history, conditions affecting some relatives, and in structured notes, any clinical finding that can be coded. SNOMED-CT enables clinical decision support. A rule might say, if a patient has any concept descending from diabetes mellitus and any concept descending from pregnancy, alert for gestational diabetes screening. This works because SNOMED's hierarchical structure. Here's how a database might store those codes. You have your problem ID, the patient ID, SNOMED code, ICD-10 code, and its description. Notice both codes are stored, the SNOMED code and the ICD-10, even though they're redundant. This dual coding approach is common in modern electronic health records. You get the clinical precision of SNOMED and the billing compatibility with ICD-10. So for final comparison, you've got an aspect in the SNOMED-CT and ICD-10. And the purpose, the clinical documentation, and the billing and classification. Granularity, you go from very high to moderate. We get frequent updates, continuous releases, annual updates, required for meaningful use. And for the practice to qualify for enhanced reimbursements for Medicare and Medicaid claims. So they're complementary. They don't compete with one another. Think of SNOMED-CT as the clinical language and ICD-10 as the billing language. Modern healthcare IT systems need both. Now let's integrate everything we've covered so far, the database management systems, concepts, healthcare coding systems, into one complete picture. Let's trace a complete patient encounter through all the systems. At check-in, patient demographics are stored into the database. We've got the name, date of birth, insurance information, demographics, address. Secondly, we'll have some clinical information like vital signs. The nurse might record blood pressure, weight, temperature. These all use LOINC codes, which we'll cover next week, which are predominantly used in the laboratory area. Then you got provider documents. The physician describes findings using the SNOMED-CT terminology in a narrative in the electronic health record. Then we have diagnoses assigned, and these are important for billing purposes. We go back to the ICD-10 CM, the codes that are assigned for billing. The labs ordered, so during the encounter, if the doctor orders some tests, we will include the LOINC codes for those tests as we're waiting for them results to be returned. Medications prescribed, we're going to use NDC codes to identify the drug products and the information specific about the dose and how frequently to take it. And then the procedures billed. The CPT codes capture what we actually did that day. Was it an office visit? Did we draw blood? Did we do an EKG? And finally, is there a claim generated? We use the ICD-10 and CPT together to provide documentation to the insurance company requesting reimbursement. And here's a simplified view of how all these codes appear in database tables. You're going to have a patient master file that has the demographics and patient identification information. Then you've got your encounter database with each visit, having information about what was found, the purpose of the visit, what was found, what the diagnoses were, what procedures were done, what the billing codes were and charges. And you got a diagnosis file that for each patient, you're going to have a row in the diagnosis file that specifies which diagnoses this patient had, usually in ICD-10 code format, but also in SNOMED codes. And then finally, what procedures. We have a procedure database that's going to tell you what procedures were done on that date. And again, using the CPT code to be sure you have a code that you can use for the billing purposes. So that about wraps it up for this week. Next week, we're going to look at a little bit more about the lab side for lab results, and we're going to look a little bit more at medications. So here's the data model you'll be working with, an entity relationship modeling. Next week, we'll formalize how to design the relationships between these tables, between these data, between the patient, the encounters, the diagnoses, medications, procedures, lab results. Each one has to be linked together, and that's what this course is all about. All of this standardization serves a larger goal, interoperability. Our goal is to be sure that we can share information among various providers, various sources of information for the patient, using the U.S. Core Data for Interoperability, the U.S. CDI, which defines the minimum data elements that must be exchangeable between systems. And it requires the ICD-10, so ICD-10s have to be in a format that can be shared. The CPT for what was done has to be shareable. SNOMED-CT, if you have that, it has to be in a format that can be shared among various vendors, electronic health record systems, the LOINC for the lab results, and RX norm for medications. When all systems use compatible codes, the patient can move between providers and their data can follow them accurately. That's our vision. We're not there yet, but standardized coding is the foundation. We're making progress. As you work with healthcare data, watch out for these common mistakes. One, confusing the ICD-10 CM with the ICD-10 PCS. What's the difference? The CM is for diagnosis, the PCS is for inpatient procedures. They're totally different systems. Secondly, using the wrong code set. CPT is for outpatient procedures, ICD-10 PCS is for inpatient procedures. So using a CPT for a hospital surgery is wrong. Overcoding or undercoding, billing for a higher level of service than is provided is fraud. Billing for less than provided leaves money on the table. Also, you need to be concerned about ignoring specificity requirements. Billing I-10 when you have documentation supporting I-11.0 is incorrect. Coding accuracy matters for patient care, for revenue, and for legal compliance. So let me summarize what you should take away from our lecture today from week 1. Database management systems provide the infrastructure for healthcare data. Its integrity, security, concurrent access, and relationships. Postgres is going to be our database tool, an enterprise-grade, open-source, healthcare-ready database system. ICD-10 CM codes the diagnoses. What's wrong with the patient? CPT codes procedures. What did we do? These systems all work together in modern healthcare. Different purposes, complementary functions. These concepts are foundational. Everything else in this course builds on this foundation. Next week, we'll continue building. We'll do the entity relationship modeling, formalizing the database design with entity relationship diagrams. We're going to go into a little more depth on LOINC, the codes for laboratory tests and clinical observations. We'll talk about the NDC, the drug classification for medications, and we'll give you a little assignment. You'll design an entity relationship diagram for a healthcare scenario. Week 2 completes our tour of healthcare coding systems and introduces the design skills that you're going to need for the rest of the course. That's the content for week 1. Do you have any questions? Remember, post your questions on the discussion board as they come up, and we'll go over them. You can even reach out to me through email. Office hours available by appointment. Your week 1 assignments include the PostgreSQL installation lab to install the software on your home system, a discussion post on healthcare coding systems, and a warm-up query. So start on the installation early. Troubleshooting often takes time. Let me share some resources for further learning. These are optional, but recommended if you want to go a little bit deeper. For database fundamentals, here are some YouTubes that I think you'll find interesting, and I've included how long each of these YouTubes are. Most of them are fairly brief. IBM Technology has some great YouTubes in a lot of different areas. I highly recommend them. The NoSQL is interesting, but it's a good explanation of the various database types. These are all freely available on YouTube. Just click the links. So help yourself to reading these and listening to these YouTubes, and um, they reinforce the things that we have already discussed. And there's a section here on interoperability, a conundrum in healthcare. And now this slide here, these are tools that you'll be needing throughout the rest of the semester. The ability to look up ICD-10 codes, CPT codes, and SNOMED codes, the browsers. These are free and open source and allow you to, as we start looking at specific examples of codes, this is critical. You have to have access to this information to be able to do your assignments and complete and understand the work that we'll go through. So I want to thank you. I've enjoyed tremendously sharing this time with you. I hope that you're enjoying learning about healthcare databases and databases in general, and we will continue our journey, and I look forward to seeing you next week.